Hi everybody, so for quiz number 11, let's jump right into redox definitions. An oxidizing agent is a substance in a redox reaction that gains electrons. So remember our discussion from the worksheet on how we were talking about oxidizing agents versus reducing agents. Well, what we're looking at is the agent is doing an oxidation on its surroundings. So it's oxidizing whatever is around it. This means that its surroundings are losing electrons. Remember, oxidizing means losing electrons. So if the agent is causing its surroundings to lose electrons, those electrons have to go somewhere, so the agent is what picks those electrons up. So the agent ends up gaining those electrons that its surroundings lost. Okay, so its surroundings got oxidized, and it picked up the electrons that its surroundings lost. Okay, so it gains the electrons. Contrarily, on number 2, where we're looking at a reducing agent, the reducing agent is the substance that loses electrons. So what we're saying by reducing agent is that the agent now is reducing whatever's around it. That means that it takes its electrons and gives it to whatever is in its surroundings. So by doing so, it in effect loses its electrons and reduces whatever it's around. Now for number 3, what's the oxidation number on the nitrogen in the NO2 molecule? So this will just be really simple as long as you remember that the oxygen carries a -2 charge. So if it carries a -2 and you got 2 of them, then that means that the nitrogen, in order to make a neutral molecule, has to have an oxidation number of +4. So just writing this out, the oxidation number of the nitrogen. Different people write this differently, but I tend to write it like this. The oxidation number of the oxygen, altogether now they have to equal 0 because the molecule is neutral. Okay, and we have 2 oxygens here. And we also know that each oxygen carries a -2. So therefore, this now becomes the oxidation number of the nitrogen plus -4, because -2 times 2 is -4, equals 0. So therefore, the oxidation number on the nitrogen must be +4. So D is the right answer for number 3. So now for number 4, we're doing exactly the same thing, but just with a different molecule. What is the oxidation number on manganese in the molecule Mn2O7? So here, we're doing the same thing. We're setting this up where the oxidation number on the manganese plus the oxidation number on the oxygen have to equal 0. And in this situation, we've got 2 manganese atoms in this molecule, so a 2 would go right there, and 7 oxygen atoms in this molecule, so 7 would go right there. Okay, so the total oxidation number of 2 manganese atoms and 7 oxygen atoms must equal 0 because the molecule is neutral. Okay, if there was a charge up here, that's what this would equal. But the charge is 0 because this is a neutral molecule, so that all adds up to 0. And now, let's just remember that oxygen will carry with it a -2 charge, or an oxidation number of -2. Okay, so we're looking at this here, 2 manganese atoms have to counteract this -14. Okay, so the number that works for this is +7. So the oxidation number on the manganese becomes +7. So +7 times 2 is +14, plus -14 does indeed equal 0. So if the oxidation number on the manganese is +7, we have 2 of them, and the oxidation number on oxygen is -2, and we have 7 of them, then they together add up to give you a neutral molecule, and that satisfies this equation. So therefore, C is the right answer for number 4. The manganese oxidation number is +7. For number 5, according to the activity series, which of the following would you predict to be the strongest reducing agent? So let's take a look at the activity series and see what it tells us. There we go. So here's the activity series that we're using from the book. And we have all of these different elements, and they are being oxidized. Okay, so here they are losing an electron. And the higher up on the table they are, the more readily this process happens. So we look here at our different choices and we see that lithium is the one that's on the top. So this is significant because what this tells us is that lithium most readily gives up its electron. It becomes lithium ion and an electron is given off. So if an electron comes off of the lithium very readily, that means that electron is now very available to reduce something that's around it. So lithium here is shown as being the strongest reducing agent. Okay, remember how we talked about how to read this table? The higher up on the table you are, the better of a reducing agent you are, because you give up that electron more readily. You come down here to the bottom of the table, you become an excellent oxidizing agent, but a weak reducing agent. Okay, so lithium here is shown as being the strongest reducing agent because it gives up its electron most readily. So let's come back to the question. So now for number 5 then, D is the right answer because lithium is the one that's on the top of the activity series, so it's the best reducing agent. Now returning to the activity series, which of the following would you predict to be the strongest oxidizing agent? So let's come back to this and see which one's our strongest oxidizing agent. We have a few, we have a few choices. We have lithium. Well, we know it's not lithium because that's our strongest reducing agent. We have magnesium, nickel, and gold. Let's take a look at those. So let's find magnesium. Here's magnesium. Magnesium and nickel. Let's look at nickel. Nickel's down here. So nickel here is shown as being a weaker reducing agent, so it's a better oxidizing agent than the magnesium because it's lower down on the table. And gold down here is the farthest down the table you can possibly go here in this table. So out of the 3 choices, of course lithium being up here is definitely not going to be a good reducing agent. Or excuse me, yes, reducing agent. So gold here being on the bottom of the table is going to be the most weak reducing agent. Therefore it's going to be the best oxidizing agent. Okay, it's going to be better than the nickel and the magnesium and the lithium. So the right answer for number 6 is gold. In number 7, we're given a reaction in which we are being asked to determine which element is being reduced and which element is being oxidized. So let's remember that here, if we're in our atomic form, both the chlorines in this molecule have an oxidation number of 0. Here we're in our ionic form, so the sodium here has a +1, and the bromine has a -1. Right? That's how an ionic bond works, right? One of the atoms has lost its electron and given it to the other. And here, bromine once again, just like the chlorine, has both bromine atoms here have a charge of 0, or an oxidation number of 0. And then the sodium chloride, just like with the sodium bromide, is the sodium and the chloride are bonded with an ionic bond. So the sodium here has a +1 charge, and the chlorine has a -1 charge. Now that we've assigned all of the charges, let's take a moment and see which of the atoms has undergone a change in charge, right? Or a change in the oxidation number, because that's what's characteristic of a reduction or an oxidation. If something did not undergo a change, it was neither reduced nor oxidized. So we need to figure out which one underwent the change, and then we'll see if it was reduced or oxidized. So since this is first here, we'll just start with the chlorine. Chlorine here went from an oxidation number of 0 to an oxidation number of -1. So it goes from chlorine to chloride. And so by having gained an electron, so it goes from 0 to -1, by having gained an electron, chlorine was reduced. So we'll just write that over here. Chlorine was reduced. So we can keep track. Next, we'll just take the sodium. Sodium goes from a positive 1 to a positive 1. The sodium was neither reduced nor oxidized because it didn't gain or lose any electrons. So sodium was not reduced or oxidized. And then lastly, let's look at the bromine. The bromine, or excuse me, here in this situation it's a bromide because it has a -1 charge. So the bromide has a -1 oxidation number, and it goes from -1 to 0. So the bromide has lost an electron and become bromine. Therefore, bromide was oxidized into bromine. So going from -1 to 0, the bromide was oxidized. Now let's see which of these our conclusions match up with. Chlorine was reduced, we agree, and the bromide was oxidized, we also agree. So in this situation, the chlorine is reduced and sodium is oxidized. Nope, sodium was not oxidized. Sodium did not undergo any redox chemistry. Sodium was +1 here and was +1 there. No electrons were gained or lost, so sodium was not oxidized, or reduced for that matter. Here we go. Sodium is reduced. No, it was not. Sodium did not undergo any redox chemistry. Bromide was oxidized. Yeah, that's true, but the sodium was not reduced, so it's not C. And then bromide was reduced. Well, we concluded that bromide has been oxidized. In fact, it's really hard to reduce bromide. You would get something like Br2 minus if you tried to stuff another electron on there. So that's not really going to happen. And chlorine was oxidized. Well, we came up with exactly the opposite of that. Here, chlorine we found was reduced because it went from 0 to -1, so it gained an electron. In order to be oxidized, we'd have to make Cl+, and that also would be very, very difficult. So it's neither B, C, nor D, so the correct answer is indeed A. The chlorine was reduced, and the bromide was oxidized. Now let's return to the activity series once again and see if this reaction here with sodium plus and zinc is going to happen. And what would the products look like? So let's take a moment and look at where our electrons are. The sodium has lost its electron already because it's sodium plus. The zinc still has its electron because it's neutral zinc. So it has an electron that it can give up. The question is, will it be willing to give up its electron to the sodium or not? And that's a question we can answer here by looking at the activity series. So in the activity series we have, let's find zinc, there's zinc, and let's find sodium, there's our sodium. So zinc and sodium. Now, sodium is shown here as being the stronger reducing agent, which means it wants to give up its electron. The zinc here is shown giving up, well, it's shown here giving up 2 electrons, but the point is that it is losing electrons, but it's not as strong of a reducing agent. So the whole value, the virtue of looking at stronger versus weaker reducing agents is to see if I combine sodium plus, that's already lost its electron, with something that's a weaker reducing agent, what I'm trying to say is, can zinc, by losing its electron, give that electron to the sodium and bring the sodium back from a sodium plus to sodium metal? And the answer to that question is no. In fact, it cannot, because it's not a strong enough reducing agent to get that electron back onto the sodium and get it into the sodium metal. Sodium 0 state. It can't do that. The only way you can do that is if you have something that's a stronger reducing agent that wants to give up its electron more than the sodium. Because what's going to happen is that an electron from the zinc is going to come into the sodium and it's going to try to attach it to the sodium, but the sodium is going to repel it away faster, or maybe not faster, but with more force. Then the zinc can apply to the sodium to put that electron there. So the sodium effectively cannot accept an electron from something that's a weaker reducing agent, because sodium right away is going to give that electron away. It does not want that electron. In order to force that electron onto the sodium, you need to have something that is a stronger reducing agent than the sodium. And something like, if you imagine lithium, lithium is the strongest shown here reducing agent, so it's going to give that electron up, and that electron will readily come onto the sodium and reduce the sodium. Because lithium is the thing that wants to reduce things around it more. You come over here to the zinc can't do it because it's not a strong enough reducing agent. So what's going to happen essentially is zinc is going to try to give up its electron, but there's not going to be anyone there to accept it, and the sodium is just going to stay sodium plus, and the zinc is essentially just going to stay zinc metal because nothing is taking up its electron. Sodium doesn't want it. And so effectively what's happening here is the reaction does not proceed. So no reaction takes place in this situation because the zinc cannot give its metal up to the sodium. The sodium doesn't want it. And the zinc doesn't have enough reducing power to give that electron to the sodium. Okay, hopefully that makes sense of how to relate the activity series to reactions like this. So if we were going the other way around, like we had on the worksheet, with sodium having the electron and zinc being electron deficient, the sodium very readily will give up its electron to the zinc because it's the stronger reducing agent. But if we're trying to go the other way, that's not going to happen. The zinc cannot give its electron to the sodium because it does not have enough reducing power. So therefore, no reaction will happen when sodium ion and zinc metal are combined. Okay, so D is the right answer for number 8. In number 9, we're taking a look at a reaction of thiosulfate, which is S2O3, and iodine, and we're trying to see how much of the iodine was originally present in a solution. So this is fairly complicated chemistry, but the thing that you need to pay most attention to is the balanced chemical reaction and how much sodium thiosulfate we had to put in there to react with the iodine. And then we're in a familiar ballpark. So let's go ahead and use those two considerations to figure out how much iodine was originally in the solution. So we start out with 35.2 milliliters of our sodium thiosulfate. Several of you, by the way, have asked me what's the difference between sodium thiosulfate and thiosulfate. There really is no difference. When you're titrating with sodium thiosulfate, and sodium is just the sort of like a counter ion. It's like a spectator ion. You could think of it as a spectator ion. It really doesn't do any of the chemistry. It's the thiosulfate that does the chemistry. So in the reaction here, we could include the sodium, the two sodiums here, and that would give you a neutral charge in the molecule. But it was just left out because it's not participating in any chemistry. But when we see that there were two thiosulfate ions applied here, then what we're saying is that there's two sodium thiosulfates in there. We just left the sodiums out, but the chemistry still remains the same because the sodiums don't really do anything in the chemistry. So just in case you were curious why they were different, they're really not. The sodium is still there, it's just it was left out in the equation because it doesn't do any interesting chemistry. Okay, coming back to this, 35.2 milliliters. Let's convert that into liters, and we'll see why in just a second, why that works out nicely. So that's how many liters of the sodium thiosulfate we needed. Okay, and we had a solution. We used a solution of 0.150 molar sodium thiosulfate. So if we're given a chemical equation like this one, where we have mole-to-mole ratios, it's very nice to bring everything into moles. So therefore, thereby we can use these mole-to-mole ratios to convert from thiosulfate into iodine. Okay, so foreshadowing that, we'll go ahead and use the molarity. And convert into moles of sodium thiosulfate. Okay. So that's going to give me 5.28 times 10 to the negative third moles of sodium thiosulfate. So that's how many moles it took. And now let's go back to the chemical equation. So we had 5.28 times 10 to the negative third moles of sodium thiosulfate. And let's relate this now to the moles of iodine. So we had this many moles, so for every 1 mole of iodine, we had 2 moles of sodium thiosulfate. So now that we're in moles of iodine, we can just very simply convert into grams of iodine using the molar mass of I2. So that would be just from the periodic table 253.8 grams of I2 per mole. Okay, and remember that the periodic table gives you the molar mass of just I, so just one iodine, and so what you need is I2, so I just took that mass from the periodic table and multiplied it by 2, representing that in each mole of I2 I have 2 moles of iodine atom. Okay, and so then that gets me now into grams of I2, and if you just do this all out in your calculator, then you would get A is your answer, 0.670 grams of I2. So it's a really neat way to figure out how much iodine you had in there. You just titrate it with sodium thiosulfate, and as long as you know the number of moles of sodium thiosulfate that you put in there, you can very easily calculate the grams of iodine that was in your solution. And last but not least, for number 10, what is the molar concentration of arsenic 3 in a solution if 22.35 milliliters of 0.1 molar potassium bromate is needed to completely react with 50 milliliters of the arsenic solution? The balanced reaction is the following. So we're going to approach this the same way that we did number 9, except just with slightly different chemistry, but the approach is exactly the same. So we start out here with a certain amount of potassium bromate. So let's convert this into moles. So we had 22.35 milliliters, and so 22.35 milliliters is just 0.02235 liters. Then we're going to take this and multiply it by the molarity. To get us into moles. Okay, and then that equals 0.00235 liters, moles of KBrO3. So now that we have the number of moles of KBrO3, we can use this chemical equation to convert into moles of arsenic. So now we see that 1 mole of bromate reacts with 3 moles of this arsenic molecule. So 3 moles of H3SO3 reacts with 1 mole of KBrO3. Okay, but we're not done yet. Let's remember that there is 1 mole of arsenic 3 in every mole of H3ASO3. Okay, now we're ready to do the calculation. So let's just cross off our units, make sure they cancel. Okay, we're in moles. The last step is to remember that, well, let me go ahead and write this out. 0.002235 moles of AS3. Okay, so now we get to just apply the molarity, figure out what the molarity is, because we had 50 milliliters of this solution. And so we just divide this by the volume, and that gives us a molarity of 0.134 molar. Just like that. So the correct answer for number 10 is B. And there you go. That was quiz number 11.